ברוכים הבאים לכנס האדם הלומד בעידן הטכנולוגי, כנס צ'ייס 2008 למחקרי טכנולוגיות למידה. זאת השנה השלישית שאני עומד כאן בפניכם, ואני מניח שניתן לראות כ-500 איש שנרשמו לכנס, ככה עומדים בפקקים אני מניח עדיין, מעין עידוד עבורנו במרכז צ'ייס לחקר טכנולוגיות למידה באוניברסיטה הפתוחה, עידוד להמשיך במסורת הזו. אני מבטיח לנסות ולהמשיך, הרמה הזאת היא לא קלה, היא צורכת מאיתנו הרבה מאוד משאבים. בראשית המושב אני מבקש מכולם לוודא שהטלפונים הסלולריים שלהם מחובים. אני יודע שכולם אומרים, בטח אצלי זה לא יקרה, אבל אז מצלצל הטלפון באמצע ההרצאה, ואז האדם מחפש בשארית כוחותיו את הטלפון בתוך התיק, וכולם כועסים עליו. אז אנא, דאגו לכבות את המכשירים. אני מבקש לפתוח את הכנס, הכנס השלישי שאנחנו כבר מקיימים, לפתוח אותו, את המושב הראשון שלו, מושב ראשון של הכנס, בברכותיו של פרופסור גרשון שחר, נשיא האוניברסיטה הפתוחה.
בוקר טוב וברוכים הבאים לקריית האוניברסיטה הפתוחה ברעננה. אני שמח לפתוח את הכנס, אני אגיד כמה מילים מאוד קצרות, מאוד בקיצור. האוניברסיטה הפתוחה, כידוע, אני חושב לרוב האנשים, היא אוניברסיטה להוראה מרחוק. המשמעות של הוראה מרחוק מבחינתנו, העיקרון שבעצם עיצב את דמות האוניברסיטה הפתוחה מתחילת דרכה, היה עיקרון שהאוניברסיטה מגיעה אל הסטודנט. במקום שהסטודנט יבוא לאוניברסיטה, האוניברסיטה מגיעה אל הסטודנט, לביתו, למשרדו, למקום עבודתו וכו' וכו'. בתחילת הדרך, האוניברסיטה כבר, בתחילת הדרך אני מדבר על תחילת שנות ה-70 בעצם, כשהגו את רעיון האוניברסיטה הפתוחה בישראל, זה נעשה באמצעות ספרים, ספרי הלימוד שכולם מכירים אותם. אני מדבר על תקופה שעוד לא חלמו על אינטרנט ועל אמצעי תקשורת שיש לנו היום. כאשר התפתחה התקשורת האלקטרונית ובמיוחד האינטרנט, כמובן שהאוניברסיטה הפתוחה הטמיעה את הטכנולוגיות האלה, אימצה אותן, כי זה התאים לקונספט של האוניברסיטה הפתוחה כמו כפפה ליד, איך אתה מגיע אל הסטודנט. היום הרבה יותר קל להגיע אל הסטודנט, ואנחנו אכן משתמשים באמצעים הטכנולוגיים, ובאמת כשזה קרה במהפכה הטכנולוגית, האוניברסיטה הפתוחה הקימה יחידה שוהם, יחידה שעסקה בפיתוח של אמצעים טכנולוגיים ובהטמעתם, והקימה גם מרכז מחקר. כיוון שהנושא הזה של הוראה באמצעים טכנולוגיים, או שילוב טכנולוגיה בהוראה, כולל כמובן הפדגוגיה שקשורה בזה, הדידקטיקה וכו', היה נושא כל כך מרכזי באוניברסיטה הפתוחה, שחשבנו שזה גם צריך להיות גולת כותרת של עשייה מחקרית באוניברסיטה. הקמנו את מרכז צ'ייס, והייתי אומר שהדגל של הפעילות של מרכז צ'ייס זה הכנס השנתי הבינלאומי שנערך כאן, ואני שמח באמת לפתוח אותו. יש לי עונג מיוחד הפעם, משום שהאורחת של הכנס והמרצה שלנו הבוקר, פרופסור ברברה טברסקי מאוניברסיטת סטנפורד, מאוניברסיטת קולומביה בניו יורק היום, היא קולגה שלי וחברה מאוד ותיקה, ואני מזמין אותך ברברה לתת את ההרצאה. תודה.
הייתה איזה אי הבנה של הסדר. שלום, מישהו אמר לי, אתה כמו עומד כבר, לא יודעים מי אתה, אז אני יורם אשת ואני ראש מרכז צ'ייס. והוטל עליי לפתוח בברכות, ואני אעשה את זה. הטכנולוגיות שאנחנו עובדים איתן היום, מאופיינות, טכנולוגיות שאנחנו משתמשים בהן להוראה, מאופיינות בערך בשלושה מאפיינים עיקריים, כמו שאני לפחות יכולתי לחשוב עליהם. אחד, שרובן לא פותחו בכלל לצרכים חינוכיים, וכל מה שצריך לעשות זה אדפטציה של טכנולוגיות, התקשורת, משחקי המחשב, הבלוגים, הפודקאסטים, מה שאתם רוצים, להוראה ולמידה. 2, הן מאפשרות אינטראקציה מאוד אינטנסיבית בין לומדים ופתיחה של חומרים, מה שמעלה שאלות גדולות לגבי תהליכי הוראה ולמידה, מחייב אותנו לשקול מחדש את התיאוריות או הגישות הקלאסיות שלנו ללמידה. והשלישי, הן מצויות בתהליך מואץ של השתנות, עד שסיימת לחקור את תהליכי ההטמעה של טכנולוגיה מסוימת, היא כבר אבסולית, אפשר לזרוק אותה לפח, ואנחנו מתחילים בתהליך מחקר חדש, והתהליך הזה הוא תהליך מאוד בעייתי, שמחייב סגנונות מחקר מאוד מסוימים, שלפעמים קשה מאוד לאנשים שאוהבים מחקרים מאוד הדוקים, עם ידיעת כל משתני המערכת, קשה מאוד להקל אותם, כי קשה מאוד לעבוד עם מערכות תזזיתיות כאלה. אני עוד זוכר לפני 3 שנים או 4 שנים כנס על למידה במובייל. אני לא יודע אם היום כולנו לומדים במובייל מטלפון סלולרי, אבל אז דיברו שזה יהיה. המצב הזה מציב בפנינו 5 אתגרים גדולים. 1, פיתוח של מיומנויות קוגניטיביות, מוטוריות, חברתיות, רגשיות, של התמודדות עם טכנולוגיות כאלה. השימוש הטכני הוא הדבר הקל אולי ביותר מהכל, אבל השימוש האפקטיבי הוא יותר בעייתי. הדבר הבא הוא שיפור ההבנה של הפוטנציאל של הטכנולוגיות האלה להוראה ולמידה, מה המשמעות שלהם מבחינת פתיחה של שבירת ההיררכיה הקיימת, הקנון התרבותי שיש בתוכנו, מי קובע מה הידע נחשב ומה לא וכו'. כל אלה, אני ער לגל העצום של הנכנסים כרגע. אני מבקש מאלה שנכנסים, פשוט תיכנסו בשקט, תלכו למושבים העליונים. האתגר הבא שאנחנו עומד בפנינו, השדרוג של תיאוריות, אסטרטגיות למידה והתאמתן לצרכים שלנו. התיאוריות הקלאסיות שלנו לא בהכרח תואמות את הטכנולוגיות החדשות שנפתחות בפנינו ומחייבות שאלה מחודשת. ומזה נגזר פיתוח של מודלים הוראתיים שעושים שימוש רלוונטי או יעיל או מושכל, ובסופו של דבר הבנה של האימפקט שיש לטכנולוגיות על החברה האנושית. כי כל השאלות שקשורות, למשל ויקיפדיה העמידה בפנינו שאלות שקשורות לידע שכולם יכולים לייצר, פה צריך לשאול שאלות על משמעות הטכנולוגיות האלה לחברה. הדבר הזה מחייב יצירה של קהילה ושפה מקצועית שאנחנו לומדים לדבר אותה בינינו, בעיקר בטכנולוגיות שצומחות מלמטה, יש צורך ביצירה של שפה חדשה, תוך קיום עם קהילות מקבילות בחו"ל. וכל אלה, זאת בעצם מטרתו העיקרית של כנס צ'ייס, להוות זירת מפגש בין קהילת החוקרים והפרקטיקנים בישראל, כי התחום של טכנולוגיות למידה מאוד מיוחד בזה, שהוא מהווה חיבור בין פרקטיקנים משוגעים לדבר, לבין תיאורטיקנים שבאים מתחומי דעת שונים ומבקשים יישום של הידע שלהם בסביבות טכנולוגיות. ואזור המפגש הזה הוא לא טריוויאלי, זה אזור מפגש כמו בין מפתחים ובין תיאורטיקנים. זה 2 עולמות, מי שמכיר את זה מעבודתו יודע שזה 2 עולמות שונים שלא תמיד מתחברים. ונדרש הרבה דיבור, כמו דיבור שאני מקווה שמתנהל בכנס צ'ייס מזה שנה שלישית, בשביל לקדם את הדבר הזה. מרכז צ'ייס עצמו, מרכז צ'ייס לחקר טכנולוגיות למידה, בשיתוף מאוד אינטנסיבי עם שוהם, יחידה לפיתוח ההוראה מרחוק באוניברסיטה, מקיימים הרבה פעילות במקביל לכנס צ'ייס, סמינרי מחקר, ימי עיון. אני מניח שרובכם איפשהו מכירים את הדברים. במרכז פעילים קרוב ל-40 חוקרים ופרקטיקנים מהמחלקות האקדמיות השונות, וכולנו מגויסים למען המטרה הזו, שכמו שהזכיר גרשון קודם, הדובדבן שבקצפת של הפעילות הזו הוא הכנס השנתי הזה שאנחנו מקיימים. אני רוצה לסיים את דבריי בתודות. תסלחו לי אם זה יהיה הרבה שמות. אני חושב שכל כך הרבה אנשים עסקו בעבודה הזאת ואני כל כך שונא את הרגשה. אני מודה לכל העשרות שעזרו בכנס, אז יסלח לי מי שישכח את שמו, אבל בראשית אני מבקש להודות לכל אלה שהשתתפו עמנו בארגון, להנהלת האופ, התומכת בארגון הכנס מתחילת דרכו בתקציב ובכוח אדם, לוועדת הארגון שעשתה ימים כלילות בארגון האירוע, בראש ובראשונה לניצה גרי שעמדה בראש הוועדה, בלעדיה לא יוצא פה שום דבר, תאמינו לי. לאוסנת צרפתי, עליזה אלרהן, דפנה גרינבוים, מורית מנדלוביץ', בועז מרמלשטיין, קרן פרצל וכן לעדי ברמן שובל, מזכירת מרכז צ'ייס. תודות למאיר יצחקי ואנשי מערך התפעול באופ, לשמעיה בצללי, שי לוי, ובמיוחד לגדי וייסמן, דודי נמי והרכזים, איתי מינץ, אלון דגן, חיים אליהו, עידו גולדפרב, סתיו אשורי, אביב קובי וטל שליכטר. לאנשי הביטחון של האופ, מרק סולבי ויניב מיסטריאל, תודה לרונית איזקוב על הסיוע בארגון ארוחת הצהריים, ולטלי שחם, עדי ברמן, תמר ברגר, ברברה נווה, אילנה פינסקי ודנה רבנים שקרוב על העזרה ברישום. ליחידת המחשב, ובמיוחד לעומרי אדמסקי, הייתי מצוות איזה קריסות ברגע האחרון של הצלת המצגות, היו צריכות להיות על הבוקר. לבת שבע אנגלברג על העזרה בארגון, להוצאה לאור, יונה לשם, רותי שלם, זאביק פרל, ערן סחרוף, ראומה שחור, צאלה קליין, שרון היוען, עדנה רובין, מנוחה מורביץ', עינב צדוק, דני גרבר, דודי קייגר, צבי שטיינר ולכל האחרים שעשו במלאכת עיצוב והפקת ספר הכנס המהודר שאתם רואים לפניכם, וכן המודעות והתוכנית. לצוות הצילום של מרכז שוהם, בועז מרמלשטיין, גבי חיון, גל אברמובסקי, עופר ויינר, ג'ורג' קושחזדה, דניאל קוזין, יניב ברמן ולאה פרנק, שעמלים על צילום הכנס ועיבוד ההקלטות להצגה ברשת, שיהיו זמינות לכולכם. אנחנו מצלמים את הכנס הזה, וכל העסק יהיה מתועד, כולל מצגות והרצאות עוד כמה שבועות לכולכם ברשת. לחברי ועדת ולאורית מנדלוביץ' על הקמת אתר הכנס. עבודה קשה השקיעה שם. לחברי ועדת התוכנית של הכנס, דני בן צבי, אבנר כספי, רפי נחמיה, סיגל עדן, מוטי פרנק, גילה קורץ, יעל קלי, גלעד רביד ושזף רפאלי. תודה מיוחדת לגילה קורץ על ארגון הטיפול בשיתוף הפעולה עם אידן, הרשת האירופית ללמידה מקוונת, שנותנת חסותה לכנס. לעשרות השופטים אשר טרחו בקריאה והערכה של כמעט 100 מאמרים שהוגשו לכנס, ואשר לצערי יקצר הזמן מלקרוא את שמות כולם. ותודה מיוחדת לחבריי בוועדת ההיגוי של מרכז צ'ייס, ניצה גרי, יואב יאיר, אבנר כספי וסיגל עדן, המצויים תמיד בלב העשייה ומסייעים בכל היבט הקשור להובלת הפעילות במרכז. ויסלחו לי מי ששכחתי את שמם במקרה וממש שלא בכוונה. And finally, I wish to welcome our overseas guests who fled the chilly American winter in order to enjoy the warm Mediterranean hospitality. Our keynote Barbara Tversky from Stanford University, and Yair Levy and Michelle Ramim from Nova Southeastern University, Florida, will present their works here. I wish all exciting conference. אני מאחל לכולנו כנס נעים. ופורה כמובן. וכעת, לא אמרתי שום דבר חוץ מקראתי ברכות. וכעת, יש לי את העונג להציג את המרצה האורחת שלנו, שזאת ההרצאה האחרונה שלה בסדרה של 3 הרצאות שהיא הציגה לפנינו טרם הכנס. פרופסור טברסקי הינה פסיכולוגית קוגניטיבית שמחקריה מתמקדים בזיכרון, קטגוריזציה, חשיבה מרחבית ושפה ותפיסת אירועים וקוגניציה, תוך הדגשת יישומיהם לתחומי מדעי המחשב, העיצוב, גיאוגרפיה וחינוך. היא פרסמה בנושאים אלה עשרות מאמרים בכתבי עת מובילים. פרופסור טברסקי עברה את מסלול הלימודים האקדמי שלה באוניברסיטת מישיגן, ולאחר מכן הצטרפה לסגל אוניברסיטת סטנפורד, בה שימשה פרופסור בחוג לפסיכולוגיה עד פרישתה. כיום היא ממשיכה לנהל מחקרים בסטנפורד, וכן מלמדת בקולומביה טיצ'רס קולג' בניו יורק. ברברה יש שורשים ישראלים עמוקים. בסוף שנות ה-60 הגיעה ארצה בעקבות בן זוגה עמוס טברסקי ז"ל, המוכר לכולנו בזכות מחקריו עם דניאל כהנמן, שזיכו אותם גם בפרס נובל, ולימדה באוניברסיטה העברית בחוג לפסיכולוגיה. בסוף שנות ה-70 הם עברו לארצות הברית. ברברה דוברת עברית מעולה, ואף שאלה אותי אם אפשר שתרצה בעברית. הצעתי לה להרצות בכל זאת באנגלית, בה היא חשה נוח יותר. היום תרצה ברברה בנושא Cognitive Principles of Information Visualization.
תודה רבה לקבלה הנעימה והחמה. מאוד טוב לי להיות כאן איתכם וגם לבלות קצת בארץ ולהיות בחברה של חברים ותיקים וחברים חדשים. אז אני מודה לכם מאוד על ההזמנה. ועכשיו אני אעבור לאנגלית. אז אבותינו בינתיים מהסטיינברג. אוקיי. I'll speak mostly on graphics today, on diagrams, graphics, external representations. And these are cognitive tools that people have created to expand their minds. Many animals, including human beings, create tools to expand their physical well-being, but as far as I know, only people create external tools to expand their minds. So as all of you know, the mind quickly runs out of capacity when we need to remember long telephone numbers or long lists of things to do. And the way we expand the mind is by using the world, incorporating the world into our minds. So, and that's what I'm calling cognitive tools. The main ones are things on paper, but there are many other means. We leave a pile of stuff by the door to remember to take it to work or wherever we're going. We tie strings on our finger. There are many ways that we use the external world to remind us of what we need to do. So cognitive tools serve many roles. They can augment memory. They expand our memory from short-term working memory of 7 plus or minus 2, or probably more realistically, 4 plus or minus 2. They help us with information processing. Imagine doing square roots without paper. So they alleviate our limited capacity working memory. Cognitive tools such as paper, diagrams, things you write in the sand, also use space to represent literal space and metaphoric space so that they can represent a wide variety of concepts. And that'll be something I'll talk about at length. They promote inference and discovery because you can look at them, re-inspect them, use all our tricks of spatial reasoning to make reasoning about other things. They're public. They're available to everybody who looks at them so that they can allow a community to look at them, revise them, make inferences from them. And as I say, I think they're uniquely human. There are even more advantages. These are just some, and we'll talk about those today. So you can distinguish two kinds of graphics or diagrams. Visualizations of things that are inherently visual, and the paradigmatic example there are maps. And these are ancient, and they're found in cultures all over the world. Then there are visualizations of things that are metaphorically visual. These are familiar to us. They're in the paper every day, in the textbooks that we use. They're graphs, charts, and diagrams. And for some reasons that are a bit puzzling, these are for the most part modern. There are very few examples before the 18th century, and if any of you have examples, I'd love to see them. It's all the more surprising because there are so many spatial metaphors in languages. Why wasn't there more use of external representations? So again, we'll talk about that more. Here are some examples of old maps. They come in many forms. This is the oldest known map. It's made of clay, found in Babylonia. It's 6,000 years old. Here is a petroglyph that's only 4,000 years old. This isn't the petroglyph, it's the drawing from the petroglyph. And you can see that it mixes perspectives. My arrow key isn't on here, so here it is. You can see that you get the overview of the road system, so you get a survey or overview perspective, but you also have a frontal view of the building, so that you get both perspectives at once. People have no problem mixing perspectives. Perspective was an invention of the Renaissance. People have no trouble thinking in multiple perspectives. And you see that the Babylonian map I showed you also mixed perspectives. It's very useful to have both perspectives. So you know how to travel from the routes, and you also know what something looks like when you get there. So many tourist maps that are modern use this. Another kind of map, this is a map used by coastal Eskimos in Greenland. They're beautiful wood carvings. They float, so if they fall out of the boat, you can catch them. And they have the indentations of the coast carved in on them. They're also reversible, so you get to one end and you can use the other. Other navigation maps, these are bamboo sticks and shells. They were used by South Sea Islanders to go thousands of miles on the open ocean where you can't see from island to island. The sticks are the currents of the ocean, which you can think of as highways, and the shells are the islands, and at least some of the people came home, right, using this. Okay, another kind of map you carry with you. This was used by North Coast Indians in North America, and you showed the cities, the relative cities on your hand, right, in different parts of your hand. So it's a map that you carry with you, just like you carry a calculator with you, right, in your hands. Okay, another map. This is a triptych. This is a map that takes you, that isn't geographically arrayed. It takes you from turning point to turning point, and it will take you from Spain to Jerusalem. This was used by the Crusaders. Okay, other kinds of diagrams. If you've been to Egypt, you've seen in the tombs there diagrams of how to make wheat, for example, how to make bread. This shows it from growing the wheat and milling the wheat and so forth to baking bread. And these again are ancient and Egyptian tombs, so 4,000 years old. Trajan's column indicating all his feats, and this is common amongst emperors to leave their marks wherever they can. This is a Chinese scroll, and it shows the journey of one of the emperors. So again, we have these kinds of diagrams and pictures that go back a long time. This is a letter, North American Indian letter. There was a Colonel Mallory who fought in the Civil War in the United States, and he noticed that the Indians who didn't have written language were using pictures to communicate. And this is a picture, it's a love letter actually, of a woman who's that totem on the top that's some sort of animal, and a mud puppy, which is her boyfriend, and you can see her in one of those tents, and she's beckoning him to come. So this is an invitation and a map of how to find her. And these were used very commonly. In fact, Mallory, after the Civil War, succeeded in getting a grant from the U.S. government to go and study these things and collect them while they were still being used, and Dover reprinted them in 2 volumes. They're a lot of fun. So this is another one, and this is something that's very common. All of you parents have experienced it. It's the Indian on the left, whose name is Big Turtle following Little Turtle, is talking. You can see the words coming out of his mouth, to the Indian on the right, who's his father, which is Little Man. That's his totem. And if you look there are 25 coins, and he's saying, send me 25 and I'll come home. So this is again familiar to any parent. So this form of communication, of visual communication, is widespread. There's now a collection of these sorts of things that were collected in Russia. I don't have that one. These are proverbs from Africa, again written in pictorial form. So those are the ancient ones, or the widespread ones. These are the modern ones. One of the first graphs that was ever made, economic data, 2 variables against time. It's showing a balance of trade. You can find these in the newspapers today with different font. They're very common. In fact, somebody did a survey of graphs in scientific journals and in popular journals like USA Today, Newsweek, Time, and found that 75% of them plot 1 or 2 variables against time. So this is very typical. Comics, I have a lot to say about that. I won't say it here, on how they tell visual stories. The one you just saw is American, lots of action. Japanese, not so much action. A lot of different viewpoints. There are interesting cultural differences in how these things are depicted, which we're looking at. Okay, some ways again that graphics augment cognition. They record information, convey information, and that's going to be the primary motif of my talk. Promote inferences, enable new ideas, and facilitate collaboration. So good graphics schematize. They aren't realistic, okay? They omit irrelevant information. They take the clutter out of things. And they often, they emphasize and simplify and even distort. So in the interest of telling a truth, they lie, okay? And this is the only way to tell a bigger truth is by lying, or distorting the truth in order to make it clear. If you think about words, they're even more brutal than graphics, right? They're even more abstract and more brutal and distort even more. So this is an aerial map of Kyoto. It makes a very bad map of Kyoto. It's very realistic, but you would be hard put to use it as a map. Here's a map, not the best map of Kyoto, but it's much easier to find your way there because it's simplified things and taken out what you need, not cluttered it. The paradigmatic example of a good map or a good tube map is the London Underground tube map. Distances aren't accurately represented. All the directions are summarized to vertical, horizontal, diagonal lines, but the tube stops are very apparent. You can tell, they're very clear. You can tell where the tube stops take you and when to change. Good graphics also annotate. In other words, they're multimodal. And this is something in contrast to the ancient ones that I showed you, which were primarily pictorial and not annotated. And we'll get into that more. So graphics consist of elements and spatial relations among them. And I'd like to say today, or like to make the theme of today, that these can convey meaning directly. in a way that words, which are symbolic, cannot convey meaning directly. So, spatial relations, I'll say a little bit about that at first. They can map information at varying levels of specificity. So they can map information only at a categorical level. So we divided the world into males and females, into citizens and non-citizens. Those would be categories, and that's preserving information only at this gross level, but it's a very common way of preserving information. One visual example of that is the spaces between words. There was a long time that English was written without spaces between words, Hebrew as well. It's much easier to read when you've got spaces between the words, and the spaces tell you this group of letters belongs to one meaning, and that group of letters belongs to another meaning. Parentheses are frames, boxes, are also ways of grouping information, visual ways of it, or spatial ways of grouping information categorically. But they're visual devices, they're instantly comprehensible. So ordinal, we preserve information in terms of lists. We might list our children in order of birth, our graduate students in order which they finished, the groceries in the order in which we're going to find them in the supermarket, outlines, trees, these are all representing information only in order, but not with the spaces between them. And finally, we have information representation at an interval level, where the spaces between them, how much taller I am than somebody else, or more likely how much shorter I am than somebody else, is important. It's not just that I'm shorter or taller. So, and these are commonly represented as graphs. So this was a study that we did before the Intifada Arishona in the late 80s with Sonny Kugelmas in Jerusalem and Atalia Winter, whose married name I've forgotten. We looked at about 1,400 people, mostly school-aged children, in the U.S. and in Israel, Arabic-speaking and Hebrew-speaking. And we wanted to see how do they represent information on paper. So we were mostly interested in the kids, and we were interested also in how writing order affects these things. So we sat next to the child. The child had a square piece of paper, and we had the child use that square piece of paper and stickers to represent information. And we were interested in whether whether they're representing information categorically, ordinally or intervally, and we were interested in the direction of increases if they were representing them. We looked at spatial information. I won't talk about that because that was very easy. Temporal information like the time that you eat breakfast, lunch, and dinner, or breakfast, arochat eser, and dinner. Quantitative information, the amount of candy you have in a hand, the amount of candy in a bag, the amount of candy in the supermarket shelf, and preference. Preference, we asked them, what's your favorite TV show or your favorite food? What's food that you hate or a TV show that you hate? And what's something that's in between? So we got it from the child. And let's see, we sat next to the child, and I would say, or the research assistant would say, let's think about the time that you have breakfast, lunch, and dinner. I'm going to put a sticker down for the time that you have lunch, and I'd put it in the middle of the page. And can you put a sticker down for the time that you have breakfast? Yofi, now put a sticker down for the time that you have dinner, and so forth. We did this with all the relationships that we were interested in. We had 2 temporal, 2 quantitative, and 2 preference, and we varied the order of breakfast and dinner. So we're interested, do the children put it on a line, indicating that they see an underlying temporal dimension, or an underlying quantitative dimension, or an underlying preference dimension. If they put it on a line, then they see it as a dimension. If they just put the stickers all over the place, then they see it as categorical and not an underlying dimension. And then we were interested in what direction do the increases go, and do they conform with writing order. So in terms of the amount of information preserved, we found increasing information preserved with increasing age. So some of the youngest kids, and the youngest kids were 4, we picked pre-readers on purpose, only represented the information categorically. They put all the stickers one on top of each other or scattered around the page, not in a line. There was a minority of the 4-year-olds, but some of them didn't see it on a line. Most of everybody else put it on a line. only kids over 10 or 12 represented interval. So only kids over 10 or 12 put the distance between Arukhat Boker and Arukhat Eser closer than Arukhat Eser and Arukhat Erev. Okay? We couldn't get the kids younger than 10 to do it. We tried very hard. We did a lot of manipulations. So we got increasing information preserved with age, from categorical to ordinal to interval, and there was also a tendency that the more abstract information was represented intervally at a later age. So the kids were better at the temporal information than the quantitative, and better at the quantitative than the preference. And that increased with age as well. So that we found the same for all the language cultures. So the Arabic-speaking Israelis, Hebrew-speaking Israelis, Americans were all about the same there and did the same. Okay, then we looked at directions of increase. And we had such a big sample, 1,400 people. I'll never run an experiment like that again. We got very significant data. And on the whole, the increase, writing order did not affect quantity or preference. Okay? Americans, Israelis, and Arabic-speaking Israelis were perfectly happy to make increases go from left to right, from right to left, and from down to up. The only thing they avoided, they didn't like increases going from up to down. Okay? That was the only thing they avoided. And this fits with expressions in the language, right? Lamala is where all the good things are, lamata is where all the bad things are. You say somebody's at the top of their class, at the top of the heap, somebody falls into a depression. So we have that vertical axis correlated. Up is good, stronger, more powerful. And this is pretty much in every language that I'm familiar with. If you know a language that diverges, let me know. Left and right are pretty much neutral. It's true that the word in English, the word in Latin for left is sinister in English. It has bad meaning, and the word for Latin and right has good meaning. But on the whole, left and right, our body is symmetric, more or less symmetric on left and right. If you ask people on the left and right politically which is better, right, each will answer differently. So on the whole, the left and right is neutral, but the vertical is not. It's loaded. And people were, as I say, perfectly happy to map either way for quantity and preference, no matter what language they spoke. However, for temporal relations corresponded to writing direction. So Americans mapped temporal relations from left to right. Arabic-speaking Israelis mapped from right to left. Hebrew-speaking Israelis were right in the middle. Okay, and we think they're right in the middle for a number of reasons. Partly because, as you know, arithmetic is taught left to right in Hebrew-speaking schools. And it's in Arabic-speaking schools, arithmetic is taught right to left until 5th grade, and then it's reversed. The alphabet in Arabic is connected and all written from right to left. In Hebrew, as you know, most of the characters are formed left to right, even though the language is written right to left. So the right to left tendency is stronger in Hebrew than in Arabic. In addition, probably Hebrew-speaking Israelis are more exposed to Western languages that are written left to right. So for temporal relations, the Arabs tended to go right to left. The Arabic-speaking Israelis tended to go right to left. Americans went left to right, and Hebrew-speaking Israelis were right in the middle. So the more important result, I think, is the result of the natural mappings using interval to represent distance, or using order to represent, using space to represent proximity in space to represent proximity on some abstract dimension. And even small children were able to use that and to do it spontaneously. So there's something spontaneous and natural about using space to map metaphoric dimensions. Okay, so how is space used meaningfully? Again, proximity in space signifies or represents proximity on abstract dimensions. So that means space is a very natural mapping. As far as directionality goes, the horizontal is neutral, maybe not quite. The vertical is loaded, up is more, better, and stronger, and we have those same relationships in spoken language, also in gesture, your high five, thumbs up, and that again seems to be pretty universal. So we looked at diagrams in textbooks. We looked at textbooks, biology textbooks looking at evolutionary trees. We got all the introductory biology textbooks we could find in the library. We looked at linguistic trees, geological eras, and so forth. And in the vast majority, usually 19 out of 20, 18 out of 19 examples, we found man at the top. And for biology, it's always man, okay, at the top. And so, you know, it's the present era, the geological era, the present era, the best thing, progress is always going upward. So diagrams work that way. I'm told that in interfaces, if you make good things at the bottom or strong things or more at the bottom, people have more trouble using the interfaces. Only the economists are perverse on this, right? Good things like unemployment goes up, right? Inflation goes up, all the bad things are going up, but we know that economists are perverse. So, okay. So, and you can mix spatial metaphors, just like you can mix perspectives, you can mix spatial metaphors. How many of you have not seen this? Everybody, so some of you have not seen this graphic. Okay. This is one of the most poignant graphics of all time. There's a man named Tufti who popularized it. It's not his graphic. It's a man named Minard. You can see his name there, a Frenchman. And it's Napoleon's Wars. Okay? And it's one of the saddest graphics you'll ever see. And eventually I'll get I can't move from here because I'm tied to the microphone. And this is not my style, and I'm not getting any arrow, so I'm going to have to move briefly, and then I'll repeat myself. This is the French border. This is Moscow, up there on the top. Okay, so we've got the French border in Moscow. If you go back to the left to the French border, look at that gray line. Those are the number of troops that Napoleon, that left France to go and take Moscow, Russia. The black line coming back, that trickle, those are the soldiers that returned. Okay, every president, prime minister should have this on their wall. Okay, so space is used in many different ways here. You have geographic space, the geography of Europe. You have space being used to represent the size of the troops. You have space there being used to represent the temperature, which was a factor in Napoleon's heavy losses, or France's heavy losses. And there's another way that space is used that I've forgotten there. But because the graphic is well designed, you can mix spatial metaphors and understand it, just like you can mix perspectives and understand it. Okay, so now I want to talk a bit about elements and how they're used meaningfully. I've talked about how space is used meaningfully to represent information in a way that people can readily understand it and a way that you can't understand symbolic words. So elements. One way that they're used meaningfully to convey meaning is iconic. They look like what they're representing. So on a highway sign, if you see deer, you know it's deer crossing. I was driving once in Austria, or rocks falling off mountains, you know to be careful. I don't know what you would do if a rock fell off a mountain. So when I was driving once in Austria, I saw this sign of a mountain and children falling off. And I had no idea I was supposed to catch them. What is it supposed to tell you? Okay. So even the iconic ones don't always explain, but they're supposed to look like what they represent. Then you have metaphoric ones where they look, there's a metaphor. So in hieroglyphic languages, you have a crown representing the king or a staff of office representing the king. Again, we use that in language. We say number 10 Downing Street or the White House. We mean the Prime Minister of England or the President of the United States. And then we finally have schematic ways of using elements, and I'm going to talk mostly about that. So iconic bear a perceptual similarity to what they represent. Metaphoric bear a conceptual similarity to what they represent. Schematic are meaningful abstract forms. So I'm going to skip that. That's isotypes. If you ever want to look at good graphic representations, Otto Neurath, he was part of the Vienna Circle and did part of this universal language Esperanto and invented those things. Okay, meaningful abstract forms. And by this I mean things like lines, crosses, arrows, and blobs. Very simple forms. And they have readily apparent meanings that are related to their mathematical or Gestalt properties. The meanings are context-specific, and I'm going to give you some examples now from our own research of how those meanings become apparent in context. So lines are one-dimensional. They are paths or links. So they're very good at indicating relationships. Okay? Anyone that's taking notes, I have papers on all of this, and I'm happy to send them. So their lines are good at representing relationships because they show links to each other. Crosses are intersections of two paths. Arrows are asymmetric lines, so they indicate an asymmetric relationship. Blobs are two-dimensional. They represent, on the whole, enclosures or areas. So they enclose something, or they indicate an area or even a volume. Let me show you how they indicate meaning. First, I want to talk about bars and lines and graphs, and this is work with a former graduate student, Jeff Zaks. Then I want to talk about arrows and mechanical diagrams. This is work with a former graduate student, Julie Heiser. And then curves, lines, crosses, and blobs and route maps. Again, another former graduate student, Paul Lee. So this is the work with Jeff Zaks. As I said, lines connect. They indicate a relationship. Bars contain and separate. So we gave people one of these, either a bar graph or a line graph, and we asked them to produce an interpretation. Later we gave them with real variables too, but now it's without variables. And our prediction was that with the lines, people would give us trends, because they would say A and B share a dimension. They just have different values on the dimension. So people are going to interpret that as a trend. However, when A and B are represented as bars, people are going to say that all the A's are in one box, all the B's are in another box, and they're separate. Okay? They're in different piles and they're separate. So they would induce discrete comparisons. And that's in fact what we got. So the trends, we got statements like, and we had blind judges who scored these, that we got statements like things rise between A and B, there's an increasing tendency from A to B, an increasing function. But when we got the bars, we got the B's are higher than the A's, or the A's are lower. There are more B's than A's, greater A's than B's, stronger, and so forth. So we got discrete comparisons on the whole for the bars, and we got trends for the lines. So then we added real variables, either continuous or discrete. So we added height of 10 and 12 years old, which is a continuous variable, or we added height of men and women, which is a discrete variable, and we again presented as bars or lines and asked for an interpretation. And the visual form was the biggest contributor to the interpretations. We got the contributions also of the particular variables, but when we had height of men and women plotted as a line, we even got subjects who said as you get more male, you get taller. Okay? Most people didn't say that. They said there's an increasing tendency for height. But when we gave a line, we got far more trends. And when we gave the boxes, the bars, we got far more discrete comparisons. We did get an effective discrete or continuous variable, but the visual overrode it. We did the reverse experiment. We gave people, let's see, my graphs are too confusing here. We gave people either trend descriptions or discrete descriptions. So a trend description for the discrete domain would be height increases from females to males, or a discrete comparison would be height for males is greater than for females. And similarly with the height of 10 and 12-year-olds, and we asked people to produce a graphic to describe that relationship. And sure enough, when we gave trends, we got lines. Again, the domain had some influence, but the biggest influence was the description. And when we gave discrete descriptions, we got bars. So the argument again is that the Gestalt properties of these bars and lines are what are influencing the interpretation and also the production. People make a very easy translation between lines and relationships and trends, and between bars and discrete comparisons. So, next example. I guess these are other examples of using, I'm going to skip that. These are networks, which actually I think networks are sort of a core of information knowledge representation, and you'll see them in representations all over. This is the ARPANET, the internet in 1987. Now you can't draw it. It's just so high. And visualizations, network visualizations of the web have become impossible. At first people tried to do them and they become increasingly impossible because they get so complicated. But these kinds of diagrams of linking nodes with lines are excellent for representing abstract information and they're used universally unless you've got too much, right? This is actually art. This is an artist named Mark Lombardi, and you can't see it, unfortunately, it takes up a whole wall, but he uses these to represent social networks, political networks, and they're quite beautiful, and people stare at them for hours trying to look at the relationships. This is an argument map. This is actually used by people in philosophy, by philosophers, to teach people how to reason. And it's based on the metaphor of support, of arguments that support an argument and are below it. They give it support from the bottom. And Tim van Gelder, who's in Australia, a philosopher, claims that he gets people to reason better using these things. Venn diagrams, another spatial way of presenting information, where sets are represented as circle and intersecting sets as intersecting circles, and again used to help inferences all over. These haven't been studied in the laboratory, but they're clearly useful. Okay. So many of these diagrammatic devices that I've talked about are useful for conveying structure, elements and relations in those network diagrams, lines, boxes, and blobs. Conveying change over time is more difficult. Diagrams are static. So how do you convey change over time? Things like how something behaves, processes, causality, decision trees, anything that happens over time. The way that's often used is arrows. And that's again an asymmetric line. So Julie Heiser and I were interested in how do people interpret arrows. Oh, first of all, arrows seem to be a natural interpretation of directionality. They are asymmetric. Arrowheads fly in the direction that they point. And if you look at erosion patterns at riverbeds, they form arrows as they go down. Okay, so that we have arrows in nature. I want to apologize for not looking over there, but if I look over there, I lose the microphone, and I'm worried about the people next door. So my apologies. So arrows have a natural interpretation of directionality. However, they have many uses. Some are for pointing. They're very much like our index finger. Labeling, and we'll come back to some of their uses in a minute. Direction in space, time, and motion. So Julie Heiser and I were interested in how people naturally interpret arrows. We gave people one mechanical diagram, one of the diagrams you see up there. There's a pulley system at the bottom. At the far left is a car brake, and at the right is a bicycle pump. Okay, you can see my English reading habits starting from left to right. And we gave people one of these diagrams, asked them to interpret it. We either gave a diagram with arrows, as you see here, or a diagram without arrows. When we didn't give arrows, we got structural descriptions. People told us the layout of the parts. They told us what parts were there and where they were relative to each other. When we had diagrams with arrows, people gave us temporal, in fact, causal descriptions. They told us what happened from beginning to end, and they went from the temporal order to the causal sequence like that. Okay? When you push down on the bicycle pump handle, it forces air into the cylinder. That opens the valve, which forces air into the tube, which puts air into your tire. Okay? So they gave us these causal, mechanical, behavioral explanations with the arrows. So without arrows, we get structural descriptions. The parts are attached to each other. They're below each other. With arrows, we get functional descriptions, causal descriptions of what happens from beginning to end. We also did the reverse. We gave people structural descriptions, asked them to produce a diagram, or we gave them a causal description and asked them to produce a diagram. And again, we got the same thing. If we gave them structural descriptions, we got diagrams without arrows, with the parts labeled. If we gave them causal descriptions or behavioral descriptions, we got diagrams with arrows. So people readily map. Here are some of our diagrams. You see on the left a car brake after a structural description. You see on the right a car brake with a functional description, showing how it works from beginning to end and with arrows. These people didn't see diagrams. They invented them from our descriptions. Our descriptions weren't bad. Okay. So arrows very readily lead people to make some inferences about causality, about change over time. Okay, so no wonder they're used everywhere. But I'm going to skip this, but if somebody wants to know about spatial ability and understanding, ask me afterward, because we got really interesting results here. Okay, our high spatials were able to make all kinds of inferences from the diagrams. They could make functional inferences and structural inferences. Our low spatials were, and these are Stanford students, so they're pretty smart. The low spatials were able to make structural inferences from diagrams. They weren't able to make functional or causal ones. So this was a separate study with Julie Heiser. It was very hard for them to make functional inferences. It was a harder task than the task I just showed you. And the low spatials were hard. It was hard for them to make the functional inferences from the diagram. They could make it from text. They had no trouble understanding causality and function and behavior from text. It was just reading it off the diagram. It's not explicit in the diagram, whereas structure is. So the trouble with arrows, right, is they have many meanings. They connect, point, and label. They indicate temporal sequence. They indicate causal sequence. They indicate direction of motion, often manner of motion, how the motion goes, movement over time, change over time. They indicate increases, decreases, forces. They're very good for representing invisible information, which is another problem with diagrams. How do you represent the invisible? So arrows have many meanings and how to separate the meanings. So in diagrams like these, which were World War II military charts, or they appeared in the newspapers, they're very much like the Minard diagram I showed you earlier. The direction of the troop movement is indicated by the arrow. The width indicates the amount of troops. Those are fairly easy to read. This is a little harder. There are 3 meanings of arrow in this diagram. It's a biology diagram. We have a project where we've collected diagrams from many, many different science and engineering texts, and we're looking at the devices that they use, like frames, boxes, the way diagrams are embellished to carry meaning beyond the visual by frames and arrows and lines. We're studying that. So here you have one use of arrow is to label. So you have foreign DNA, it's pointing to what it is. You have transient opening, it's pointing to an opening. So that's labeling. At the very top, you can see those little red things going into the cell. That's the foreign DNA invading the cell. So that's indicating movement. It's another use of the arrow. The third use is where you see regrowth of cell wall. That's indicating the next step in the process. So there are 3 meanings of arrow right in this one diagram. They are not disambiguated. I don't know any biology. I got it. I just explained it to you. Nobody said that I'm wrong yet. So you can understand it. However, we collected examples from science diagrams all over. You can't tell what these arrows mean. Do they mean the next step? Do they mean movement? Do they mean process? It's just, they're beautiful. This one is the rock cycle geology. It's gorgeous. I have tons of examples of these. You simply can't disambiguate the arrows. Here's another rock cycle, more abstract, same problem. This is how you pass a bill in the U.S. Senate. Okay, so it's not just science, right? There's no way you can disambiguate this. So the problem with arrows is they're too useful, and how do we disambiguate them? Clay used arrows in his art. He had a whole theory of how they're used. So I'm going to skip that, if I can. So we've studied, I'll come back to the ambiguity problem in a minute. I want to tell you a little bit about ongoing research with Angela Kessel, and this is on cycles. And this would be interesting to replicate in Israel, although I think you'd get similar results. We had people create diagrams of cycles and understand diagrams of cycles, but we gave them a cycle with boxes in it. And we found that there's a bias to start reading the cycle from 12 o'clock. If it's not clear, if the cycle doesn't have a natural beginning, you start reading from 12 o'clock and go around clockwise. If the cycle has a natural beginning, you begin from like a single cell stage, you begin from the beginning. Similarly, if we ask you to produce cycles, you put the first stage at the top. However, the more interesting result was when we didn't give people these circles, and we gave them processes four processes, things like even winter, summer, spring, fall. Winter, spring, summer, fall. Or we gave them, you wash clothes, you get them dirty, you put them away, you wash clothes, you put them away, you wear them, you get them dirty, you wash clothes. So there's 4 cycles again, 4 steps to the cycle. We ask people to form a diagram of those. We don't get cycles. We get lines. Okay, and we've run this over and over again because we just couldn't believe it. Even with the seasons, people want a beginning, middle, and end. They don't like these things that keep going in a circle. So this has educational implications. We're just beginning to explore them. So I'm gonna go. How much time do I have? 20 minutes. 20 minutes. Okay, I'm okay. So I want to talk a little bit more about these schematic devices, because route maps are an excellent example of very simple schematic devices that form a kind of vocabulary for making route maps. And we think you can do this for other domains. Find a simple visual vocabulary and create a visual language and rules of combination and form simple diagrams that are easy to understand. The advantage of route maps is we've been making them for generations. So they've been fine-tuned by this informal user testing that I make them and you understand or don't understand, and then I correct it, and so forth. So we looked at route maps, we asked students to produce them, and we got things like this, where things are heavily simplified. So maps could be analog, but people simplify them to curved roads or straight roads. They simplify angles to right angles. They don't represent distance accurately. They expand distance where you have a lot of turns. They shrink distance where you just go the long way in the highway. This is all very sensible because it's matching your mental map of how you need to go to get somewhere. So we found, here's another example, and we've got verbal instructions. They all map onto this simple vocabulary, which maps on to a simple verbal vocabulary. You have several forms of turns, full intersections, T intersections, L intersections, straight paths, curved paths. You have landmarks that are indicated by blobby things or names of roads, and about half the time you get arrows. They're not necessary. And people can use this simple visual vocabulary to create on demand all sorts of directions. You don't need anything more than that. Okay, so it's a very simple vocabulary. Again, we think that it can be applied to other things. It also translates nicely into words, so it indicates that the same mental model is underlying each of those. I'll show you in a minute that it translates into gestures too. Okay, so both they're parallel, the descriptive or verbal elements and the depictive, suggesting the same underlying representation. Both toolkits, verbal or visual, is sufficient to create directions, so in that case we could do automatic translation. So then the question becomes, why do they work? Because they're distorting things, right? They're lying. They're telling you things that aren't quite right. They're presenting misinformation. The reason they work is the reason that any communication device works, including the words I'm saying now. I mean, part of the reason the words work is I'm pointing to pictures, right? And I'm gesturing. They work in a context, right? They work because people fill in a lot of information from the context. So if you're driving and you think a turn is 90 degrees and it turns out to be 120, you're going to go the way the road goes, right? You're not going to make your own road. Similarly with distance, you don't need to know the exact distance because you wait till you get to the landmark and then you turn, okay? So that any kind of communication works in a context. It relies on some sort of user understanding. That's why experts are better in domains than novices. But the schematization, the simplification, the distortion makes the communication much easier and clearer. Okay. So from this you can get cognitive design principles. From the work that we did on maps, and again I think this is an exercise that you can do in many domains. We're doing it now with meteorology, with the water cycle, and we're doing it with precipitation and chemistry. We think it can be done in many domains. And for route maps, we know paths and nodes are important, exact distances and exact directions, angles are not. And some computer scientists down the street, a couple of graduate students, much smarter than we are because they knew how to make money from this. We didn't. So they developed an algorithm on the right for generating route maps for drivers. Normally in the States you get out the map on the left. It gives you way more information that you need. It doesn't give you the information you do need, getting on and off the highway. So they're very difficult to use. They're almost no good. The one on the right blows up the information you need, shrinks the information you don't need, going all that distance on the highway, makes the turns at landmarks very explicit, and in beta testing, 96% of the users raved, okay? And now you can find that, I don't know if you can find it in Israel, but you can find it on MapPoint, which Microsoft bought it. Manish Agrawala went to work at Microsoft, and so forth. By the way, I couldn't find Google Maps on Israel. Is that my problem, or there isn't? There are? Google, okay, I just couldn't find it. Okay. So here are some gesture studies. We've had people gesture these routes. They form a narrative as well as a step-by-step. So there's an introduction, they wave, or this guy at the lower right is doing you are there. He's pointing to you and putting where you are on the map. He can't use words. He's only using gestures. They point to landmarks. So landmarks are point-like things. They're there, and he's pointing to them, or all three of them are pointing to landmarks. That's mapping onto our little blobby things. They trace paths, right? These are iconic gestures, not didactic ones, and they're mapping onto the shapes of the paths. So again, the gestures are mapping very nicely on the words and on the diagrams. It's not moving. Okay, and they end. They show you, I think I skipped one. No, I don't have one more slide. And they end. They show you when you've gotten there, right? There's an ending. So that the gestures map onto the diagrams, map onto the language. The same semantics underlies them. There are different rules of syntax, and again, it's something that we've studied. So effective graphics are created in communities that use them, just like spoken language is. And they undergo this natural user testing, and you can short-circuit that process in the laboratory by having cycles of production comprehension. Okay, these schematic elements that I've talked about, the lines, bars, blobs, trees, are a visual vocabulary for diagrams. They go beyond the iconic and metaphoric, and they are like schematic spatial terms. So lines and arrows are like words like connection and relation. Bars are like words like container and frame. Blobs are like words like fields, region, area. These are all spatial terms. All those spatial terms have many uses. They suffer from the same ambiguities as the diagrammatic elements, and we count on context to disambiguate in both of those cases. So is it a mathematical relationship or a romantic relationship? Right? The context disambiguates. And are we talking about a field of study or an electric field or a mine field, right? We again, count on the context to disambiguate those terms. So again, this visual vocabulary is very similar to the verbal vocabulary, has many of the same advantages of being useful in schematizing the information, simplifying it so that it's more understandable, but also the inevitable ambiguities and errors due to that. So again, Steinberg is the master of this. This is a diagram. This is one of his visual jokes. It takes up about twice the space here. I once saw it at a gallery in New York. It's wonderful. At the far left, you see Steinberg drawing a line. So now go back to the far right, and you see the line changes meaning. It's the same line. At first, it's the ceiling. Then it becomes the tabletop. Then it's a railroad bridge. Then it's the Nile. Then it's the sidewalk looked down from above. Then it's a clothesline. Then it's the Grand Canal in Venice. And then it's Steinberg drawing it. And the line changes meaning. But you have no trouble in the context, and because Steinberg is a master, understanding what it means at each point. Okay, cognitive principles for effective graphics. I'm going to go 5 minutes over time. Well, we started at 20 after, so I'm still okay. So cognitive principles for effective graphics. One is a principle of congruity mipui, mapping, that the structure and the content of external representation should match the structure and content of a desired mental representation. So the simplest example is a map. A map shrinks the world but it also simplifies the world. So the places on a map are represented on the map, the spatial relations between them. And if you have a metaphoric map, preference, how much do you like something, that's mapped metaphorically, again on distance. So congruity is especially about structure and the mapping, and that should be transparent and readily comprehensible. Well, so the second principle is apprehension, that the structure and the content of the external representation should be readily and accurately perceived and comprehended. So it's not enough that it's there in paper, it has to be simple enough that people get it. So an example where people don't get it is that aerial map of Kyoto where you can't see the roads because it's so complicated, even though everything's there. So that brings us to animation. And because and according to the principle of congruity, animation should be good because they use change over time to represent change over time. Okay? So everybody jumped on the animation bandwagon, and for good reason. They seem to be congruous. The mapping seems to be good. Okay? But animations have a problem, and one of the problems is they're hard to perceive. So the world presents us with animations. We're constantly watching things in motion. But try to think, how do you walk? Where exactly do your arms and legs go when you're walking? Okay, when you start to think about it, you can't walk anymore because you don't know, okay? This is one of the examples first examples of stopgap photography, of showing how horses' legs gallop. It was done to settle a bet on whether all four legs are off the ground at the same time. No one could see that when a horse galloped. The art galleries of the world are filled with paintings, beautiful ones, of horses galloping wrong because people watched them but didn't know how they worked. We watch rainfall. It doesn't mean we know how it works, right? Or how it happens. We watch animations all the time. We don't understand them, okay? It wasn't until the stopgap photography, and by the way, all four legs are off the ground at the same time, that people knew. This was done at Stanford, by the way, on the Stanford Ranch. So I'm going to show you an animation. It's beautiful. I got it off a website years ago of good animations. Okay? See if you can follow it. I hope it works. Yeah, it works. It's beautiful. Okay, but you can't follow it. You can't see what valves are opening relative to what other valves, when the things are changing color, what's going up and down when. Even if you watch it over and over again, you can't get it. Okay? And it turns out there have been dozens and dozens of studies using animation, comparing them to static graphics. Most of the comparisons aren't good. When you whittle it down to the comparisons that are good, in other words, the same information is in both, and you don't add the element of interactivity, which has its own set of issues, there isn't a single case where animated graphics are better than static. And this is for a wide range of material, from abstract material like learning computer algorithms to concrete material like learning how one of these pumps work. You can look at any kind of mathematical algorithms, again, mechanics, physics, biology. There isn't, I mean, I'm not totally up to date in the literature, so maybe there are some by now, and there are cases where the animated graphics are worse. 10 minutes, I'm fine. Where the animated graphics are worse. So this we discovered, Julie Morrison, a former graduate student, Mireille Betancourt, a French postdoc who was working with me. We did a big review of the literature. We were shocked ourselves because we thought animation should work. And in fact, Julie Morrison's dissertation was taking a very simple animation, just a ball, going on a route very slowly. Even there, the static graphics were just as good as the animation. Okay, and we think we could have gone even farther and shown that the static graphics were even better, but we thought it was actually trivial. But so even with very simple things that are easy to apprehend, it's not clear that you get any benefit from animation, and I'll tell you why. And we puzzled on this for a long time. So one issue is the apprehension principle. Animations are hard to perceive. Too much happens too quickly. But even when you slow things down, you have like that ball moving very slowly, it's not clear you'll get advantages. And there I think it's because animations are conceived of as discrete steps. Think about a route. The route you want to think about is go here, turn right, go there, turn left, go straight down, turn right again, go around the traffic circle, right? You don't need to know all that happens along the highway between. And it would be ridiculous to show you that. All you need is those turning points. What actions happen at what turning points? The same goes for abstract events. You want to explain how that carburetor, or whatever it was, that pump worked. You want to know what's happening at each of the junctures where things change, exactly what's happening. So you want to give people the discretization. You want to give people the sequence of steps. The way we understand even everyday animated events, this is work with Jeff Zaks and Bridget Martin, we've studied how people understand everyday events like fertilizing a plant, making a bed, doing the dishes, putting a saxophone together. We've studied many cases. We've had people describe what goes on in those situations. They describe discrete steps. Actions are the objects at discrete steps. Okay? And that's the critical information, and you want to give people that. So why make them infer it? Right? Why should they go through the job of being a scientist, where we have millennia of human beings not understanding how rain falls or how seeds grow? Why not tell people, right? Let them same with a route. You don't make them discover the route. You tell them the route, where to turn. Okay, so events are perceived as sequences of steps, so it makes sense to discretize, make that sequence of steps explicit to people. You can do that often in static diagrams that are caught at the discrete steps that show you the turning points. So even a pulley system, which operates continuously, this is work of Mary Hegarty, is conceived of discretely. People describe it as the action of each of those pulleys, and when people have to make inferences of which pulley goes which way, they animate it from beginning to end. Okay, the reaction time data shows that. They don't even go from end to beginning, which they could do. If they're asked about the last pulley, all they have to do is think about the weight going up. But they don't. They want to think about the process from beginning to end in discrete steps. So animations use change in time to convey change in time, so they're congruous, but animations are hard to perceive. They're conceived of as discrete steps. The third reason why the animations that are mostly available now don't work is they're not explanations. Showing isn't explaining. Watching rainfall doesn't tell you how it happens. You have to explain. What do we do when we explain? We slow things down, we speed things up, we zoom, we change perspective, we use analogs, we go microscopic and tell processes, right? We add all kinds of extra information. We show graphs of how things change if we're describing chemistry. So a good explanation happens in time. So in that sense, it's an animation. But that's the kind of educational animation we need to make, is one that that uses discrete steps, that's easy to perceive, and that incorporates explanatory information into the animation. Okay, and that's what we do when we teach. Okay, some ways graphics communicate. We've talked about recording information, conveying information, promoting inferences. We've shown how arrows promote inferences, how bars and lines promote inferences, enable new ideas. I'm fine. Enable new ideas. I'm going to give you a few examples there. This is an example that's gotten more and more famous. Tufte reproduced it. The statisticians always knew it. And now last year in the States, or 2 years ago, a whole book was written about this graphic. This is Snow's a solution to the cholera epidemic in London in the 1830s. This was before a germ theory of disease. Nobody knew how you got cholera. There were all kinds of mythic interpretations of how you got cholera. Snow took a map of central London and he put a dot wherever there was a case of cholera. He looked at the map and he saw that they were concentrated around one water pump on Broad Street. Nobody knew the water carried cholera. He said, take the pump handle off the pump and the epidemic stopped. Okay? It wasn't quite that dramatic. But these kinds of maps are used in epidemics. They're the tool of epidemiology, right? Is tracing where diseases go, right? And then you can find out that they came from some chickens in Vietnam, right? The flu. Okay, so this is a matter of inference. Here's another example. This was in World War II, bombers going from England to Germany. Many of them were not coming back, some of them were. There was a small amount of money to reinforce the bombers, and the question was, where do you put the reinforcements? So the plane on the left this is Wald who solved it. The plane on the left represents, before there were any, it's an empty plane. Then whenever a plane came back and was hit, they put a black dot on that white diagram. They eventually ended up with a diagram on the right. Okay, so where do you reinforce? Exactly, the white. You guys are smart. The class I taught last week, they said the black. The black are the planes that come back, right? You don't need to reinforce them. They got back, right? You need to reinforce the planes that didn't come back, and that's where the white is. It happens to be where the pilot and the co-pilot are. But so that makes sense too. You need the human mind there. But this is, again, an example of using diagrams to make inference and reasoning. Up until now, we've talked about diagrams that we wanted them to be crystal clear. In fact, we wanted them to lie in order to be clear. There are cases where diagrams, you want ambiguity. And this is in design. Design is a prime example of that. And that's in early stages of design. This is an actual architect in one of our studies designing a museum. And you can see, this is actually pretty much far in the design, but you can see it's very tentative. Designers don't like CAD programs because they rectify everything. They make everything too rigid already. They want blobby stuff. They want to see, well, let's put here, this, there. Let's see what it looks like. What's more, when they look at their own diagrams, they put things in for what purpose? But an experienced architect will see things there that they didn't intend. And they'll make new discoveries. They'll see patterns, they'll see road traffic, and so forth. So they want the ambiguity. So there are cases of inference making where you don't want things too perfect because it freezes you to one set of ideas. We got some spatial ability differences here. I can talk about that later in making interpretations. Who's good at it? Facilitate collaboration. We've done a number of studies looking at people working over a diagram, creating a diagram to solve a problem. You can do this for concrete things like routes, abstract things like planning, organization, structure. When you have a diagram you can both share, people like the collaboration better, they think better on it, they think the better on it. What's more, the diagram becomes a shared product. It's something that they both do together, and so it's not yours or mine, it's both of ours. So it becomes our joint product. We're not against each other, we're a team. So diagrams, gestures on them facilitate collaboration. This is one view of it. So why do diagrams communicate effectively? One way they communicate effectively is that the elements are readily interpretable. The icons, the figures of depiction like the metaphoric icons, and the meaningful abstract forms like lines and bars and blobs. They are readily comprehensible and people understand them. Another reason diagrams are effective is the mappings are meaningful. We've seen the time, value, strength. They're all spoken about in terms of spatial metaphors. So they're all readily, a powerful leader is up. Those mappings are meaningful. People readily understand them. Also, spatial inferences are easy. We've been making spatial inferences all our lives, probably before birth, right? And we can take those tools of making inferences about direction, category, distance, and apply them to diagrams. So they're not always correct. I've had another career looking at the errors in spatial reasoning, but we're better at spatial reasoning than other reasoning. So even though we make errors. So those make it easy. So those are all reasons why diagrams communicate and interfaces communicate correctly. So I'll leave you again with a chokmah of Steinberg, and thank you very much.
תודה רבה לברברה. אני רציתי רק להציע לכל מי ששאל, אבל איפה הטכנולוגיה? לומר שבתוך ההרצאה היו חבויים המון רמזים על שימושיה של טכנולוגיה, על האופן שאנחנו מייצגים אינפורמציה באופן חזותי, כך שנוכל לפרש אותה, שאלות שקשורות לייצוג חזותי בעולם שנעלם. לא מזמן עשינו סקר עם ילדים, שהסתבר שהאייקון של דיסקט, לא אומר להם שום דבר. זה האייקון שנעלם מן העולם, כי הם לא מכירים, מעולם לא ראו דיסקט, אבל עדיין אנחנו מייצגים את העולם. כל השאלות שקשורות לייצוג חזותי, שהטכנולוגיות מאפשרות לנו ייצוג, עלו כאן בהרצאה הזו, על אף שהיא לא, המילה טכנולוגיה לכאורה לא נשמעה בה.